again, based on the 98 paper. Let's do this. And let's try to see if I can get it done by the break. Yeah, let's do this by the break. So in 18 minutes, we will get the key out of an RSA using a timing attack. Awesome. So we have a signing key, we have a verification key, and the device is doing a signing operation. And we know N, and we know it's Montgomery, and we know R, and we know all that. And we send a lot of queries to the device, the smart card. We're saying, pay me a cent, pay me a cent, pay me a cent, pay me random. We get a lot of messages, and you see that the model here is not adaptive chosen plaintext, but in fact it's known plaintext. So I'm going to collect a large amount of traces, and I kindly ask your attention to the dimensions here. You see there is a K here. So I'm going to collect K traces. And each trace is going to contain the message, the signed message, which I'm just going to take and throw away because I don't really care, and the time it took me to do the calculation. This is my online data collection step. Okay, so is this clear? This is what I'm going to do with the device. I'm going to do K measurements and generate a trace size K of what was the message and how long did it take this device under test to sign it. And in contrast to the homework assignment, this is going to be non-adaptive. I don't really care what the messages are as long as they're nice and random. Of course, probably somebody wrote a paper on what's the right way to choose them, and you can look for it yourself. This is all. Okay, so I have a question here. Question is, which time is it? It's 6:44. No. This means how long did it take from the time I sent the message to the time the smart card returned the signature? And it's my attacker time. No? Which? What? No, we're doing this once. We're doing it. We're going to take the set of K measurements and get the entire key out of them. We're not doing the attack yet. This is what's called the online phase. First of all, we collect the data. We collect the data. It might be very risky. We collect the data, and then we go home to the lab with a sack full of traces. This is even before we start extracting the key. Okay? Because the presence or absence of this extra A times M is only dependent on the Hamming weight of the secret key. You can't vary it. Okay? No, there's M1 is the one message, a long message, a bunch of bits I ask the device to sign. M2 is another long bit of a bunch of bits. This is a number. It's a number inside the multiplicative group, which is representing the message. Okay. Okay. So now I have a data set with message, time, and I have K traces. Now I'm going to go to the induction step. And the induction step is I know a bunch of bits in the key, and I'm trying to guess the next one. And now I'm going to simulate. So I can simulate, as I showed you in the chat, I can simulate all of the bits I know. And then I try to see on the next bit I'm guessing which one of the messages gets an extra reduction. So I can simulate, again, I'm looking at the shared notes, I can simulate. Can you see if I'm highlighting? When I'm highlighting, does it appear highlighted in your text? Or no. So I can try making it maybe. I'm looking at the top part. I just made it italic. So this is completely known to me because I know the key so far. And there are two possible options. One option is that the key bit is 0, and one option is that the key bit is 1. So if the key bit is 0, First of all, I say, what if the key bit is 0? And then I can simulate one extra step for each one of the messages. And I say, if the next key is 0, then I have a bunch of messages here that got an extra reduction, this subtraction. Okay, because now I can simulate them one more bit. Okay, but what if the next key bit was 1? Then I have a different group which got an extra reduction. And if you notice here, they are not mutually exclusive. They don't have to be the same size. It's just, I'm just doing a simulation with a different guessed key. So now I have 2 simulations. And of course, after this reduction happens or doesn't happen, then the device center test has to do all of the other extra cryptographic. It has to process all of the other bits in the ciphertext and then do the modular reduction in the end, and then do whatever else it's doing. But there is a little contribution. If the next key bit is 1, these messages need to have an extra reduction, and these ones don't have an extra reduction. And if it's 0, these messages have an extra reduction, and these ones don't have an extra reduction. And now I take my data structure and I split it this way. And this is a very important step. What I did is I said, if the next key bit is 0, then according to my simulations, these messages get an extra reduction, and these ones don't get an extra reduction. But if the next key bit is 1, these get an extra reduction, and those don't get an extra reduction. So what am I saying? That if I got the key correctly, then the running time of this bunch should be different than the running time of this bunch. If the key bit is 1, then the running time of this bunch should be different from the running time of this bunch. And now let me ask you a question. If the key bit is 0, key bit is 0, and I divide my messages into 2 groups according to the assumption of 1. Of course not. It's the most difficult thing in the course. If I guess the key wrong, and the key is actually 0, but I think it's 1. I guess it's wrong. And I split my messages into 2 groups according to my incorrect hypothesis. Will there be any difference in the running times of this set and this set? Assuming I have a wrong key guess, will there be a difference in the running time? So, okay, you're doing your best, and I appreciate it. I really appreciate it. So, if I guessed the key wrong, then I'm just going to take this bunch of running times and take a completely random, hand-wavingly, completely random split. I'm going to split them into 2 groups based on no reasonable metric. My split is meaningless. And in both cases, I'm actually sampling from the same set. So the statistical properties of this set are going to be equal to those of the other set. So I should find no difference in between the 2. If I guess the key right, there will be a difference. If I guess the key wrong, there will be no difference. I just want to do the extra step here and say, okay, if the next key bit is 0, then this set should be different than this set. If I guessed 1, then this set should be different than this set. Again, if I guessed 0 and I look at the wrong set, they should be very, very similar to each other because they're just sampling from the same distribution. And now Alseni is asking, why don't I create a group by the first bit in the same? So what you're asking is, if I have an ability to do adaptive chosen plaintext, will this make my attack stronger? And the answer is possibly, but this attack works pretty well. You can use, you, of course, I will be happy to. You can reuse the bunch of k traces you created over and over again for each one of the bits. You're just simulating more and more and more. But yeah, in theory, you probably have some kind of advantage if you use adaptive chosen. So now the question of Tomer is, how did I create the groups for each case? What I did is I guessed, I simulated all the keys I know, all the key bits I know, and then I was left. I'm just moving back to the notes. I was left with the next bit I didn't know. I don't know what's going on with it, and I can simulate it in two different ways based on my keybits. So if I guess that this unknown keybit, which I'm trying to track now, is 1, if I guess that it's 1, the simulation is going to proceed in one way. If I guess that it's 0, the simulation is going to proceed in a different way. And Koch's insight was that I can tell which one of these assumptions are right. So now, there are two ways of doing this now. The way which Koch did it, which was the engineering way. And this is what we're going to get done by the break. And there is the scientific statistical way, which will be the conclusion of this meeting after the break. So let's just talk about how Kocher did it. So if you look at step 5, I have 4 groups of numbers. I have this group and this group, this pair of groups, T1, 1, 2, 4, 5, 7, and 3, 6, 8, 9. This is one way of splitting the traces. And I have another way of splitting the traces, 2, 3, 5, 8 versus 1, 4, 6, 7. And I'm trying to find out which of these ways of splitting the traces into 2 groups is the one which gives me the most statistical difference between the 2 sets. So what will I do as an engineer? Let's see if somebody can figure it out. How do I know which one of them, which division here divides better my set of traces? What is the tool I'm going to use? Okay, means, comparing. Okay, mean, right? Median. Okay, difference. Okay. T-test. Hold on with the t-test. Okay, data scientist. Hold on with the t-test. So I'm going to tell you what Kocher did, and then after the break we'll do the statistical. So we have a bunch of running times here. Let's call this. Oh, I can also draw. You're doing it so happily. I'm going to call this one. This one is, let's say, this is blue 1, and this is blue 2. Yeah, blue 1 and blue 2. And this is going to be, of course, red 1 and red 2. That's orange, actually. Red 1 and red 2. Red 2. So I am going to take blue 1. I'm going to calculate the average of blue 1. So I'm just going to write this in my share notes. Method. I'm going to take the average of blue 1. I'm going to take the average of blue 2. I'm going to take the average of red 1. I'm going to take the average of red 2. Now, I am going to do the following thing. I'm going to say the difference of means 1 is you don't actually have to do the, let's skip the average, skip the absolute value. And then I do this difference of means. DOM is difference of means. Great. So what do I do now with the difference of means 1 and difference of means 2? Any idea? Okay, let's see what are the guesses here. I compare them. Okay, fine. Okay, so if sum 1 is greater than sum 2, then p bit is equal to autocomplete, autocomplete, autocomplete. Right. Okay. Who understood what's going on here? Who understood? Okay. Right. So some people are optimistic about it. Let's this is not statistics, this is engineering. Of course, well, what am I doing here? Very hand wavingly, because this is an engineering solution. If I was able to separate my timings into 2 groups, then they're going to have a different mean. There's going to be a large difference of mean. If I wasn't able to separate them into 2 groups, then the means are going to be very, very close together. And now I just check and see which one of the 2 simulations gives me the best difference of mean. And then I can just say, this is the correct key bit. And then, of course, what I do is I continue in this in recursion, in this, not recursion, induction step until I get to the end of the key. I have a question in the chat. Will there not be an exponent? There will be a very, very large standard deviation in these groups. And what I showed you now is very bad science. It's very creative. I mean, it's not very bad science to invent it, but it's as if I would go to my boss. I'm a security engineer. I'm going to my architect, and I'm telling the architect, listen, I did the distance of means, and I found out that the distance of mean of this bit is greater than this is the mean of that bit. Oh no, we have to redesign our product. We have to make it twice as heavy. We make it 3 times as expensive. The systems engineer will say, no, you didn't explain. You didn't prove to me. How many measurements do you need to take? How confident are you in your measurements? How many measurements do you need to get the key out? What is the effectiveness of your defense, and so on? And this will not work unless we do some advanced statistics. Now, the first steps of the attack, again, don't